What if your RC system could build itself? Sounds impossible, right? Well, the truth is it's not. And I've just built a library that lets the ESP32 discover, configure, and verify the entire RC link automatically and literally in seconds. It's the kind of automation that once you try, you'll never go back. Welcome to more Little Man Builds. We'll break today's video into 3 parts. Part 1 is a full demonstration and overview of the library within the Arduino IDE. Part 2 is a quick overview of the remote control, including why I've selected 10 channels and also how I plan to use it within the car project. And Part 3 is how we integrate this into our existing RTOS code. Let's crack on. So the first thing we can do is go down to the library icon, and we're going to search for the library called RCLink. We're going to install this library here by Little Man Builds. And we can install it with dependency. Arduino JSON is a useful addition and definitely will benefit this library a lot. So we hit install all. So successfully installed. Next thing we can do is head down to the example sketches and we'll choose the first one, iBUS calibration. In terms of setup, this is the simplest sketch ever. All you need to know is the input pin for your iBUS signal, which in my case is pin number 18. We're going to send this to the ESP32. And we'll come back when it's loaded. So perfect, it's now uploaded correctly. So let's bring in the serial monitor. And what I actually will do is reset the board so that we can see the full sketch. And all that we need to do is that we ensure that our remote control is on. We can move the sticks slowly to all the extremes and let them return to the center. We can turn all the knobs, flick all the switches. The order is not important, but the main thing is that we cover off on every single channel, pressing any key to begin sampling the data, and then again, pressing any key to stop sampling. So let's do that. So there's our remote control. Let's turn it on. And let's press any key to begin. So it begins sampling. So let's do channel 1 and 2. We'll move it to the extremes a couple of times, just nice and slowly. Doesn't matter which direction. The main thing is that it's moving through the axes, up and down, nice and slowly. We do the same for this stick. You could have chosen to move the sticks in a different way. To the potentiometer. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. And each of the switches. This is the 3-way switch, so it has a middle value. Just going to do this one twice. And then we press any key to finish. So let's have a look at the data in a little bit more detail. All it's done is it's gone through a series of values that it's picked up from the iBUS. Then for each channel, it's created a span in terms of the microseconds that it's seeing, grouped them into clusters, and has a total amount of samples that it's taken. It then provides suggestions, whether in the standard format or in the format of JSON, which I honestly believe is a little bit easier to work with. So all we now need to do is copy our JSON values. So we take the first brace all the way down to the bottom and press Ctrl+C or copy. We head back to our library, the JSON config demo sketch. So let's open this. Now everything in this sketch is already configured for a general output from the iBUS calibration sketch. So I don't need to redefine the channel names, although you could. In that case, you would also then need to change the map values here. But for us today, we can simply paste in what we received. And here you can see that for the axes, these are generic values. So going from -100 to 100, you can change these to whatever you like. So for the variable potentiometers, I can change this from 0 to 100. Also for channel 3, I can change this from 0 to 100. And all our switches look accurate. So we've got 2-way position switches and the 1 3-way position switch. So that seems to all be looking good. Just again, check your iBUS signal pin, which for me is still pin 18, and then we can just hit upload. And it's honestly as simple as that. So let's bring in the remote control again. We'll turn it on. And let's open the serial monitor. So now we can see our channel values coming through. And when I play with the remote control, channel 7, channel 8, channel 9 is a 3-way switch, channel 10, my 2 potentiometers, there we go, the remote control's configured. So let's quickly look at my remote control. It's a Flysky FS-iA6B with 10 channels. It wasn't cheap. It was approximately 100 US or 90 euros at the time of filming, and I could have opted for a 6-channel being slightly cheaper, but I wanted some extra flexibility and control to the car. Let me quickly explain. So channel 1 will be steering. Channel 2 will be forwards or backwards. Channel 3 will be overall speed to the wheels, and channel 4 could be for indicators or something like that. Channel 5 could be for the internal car volume, and channel 6 could be for the overall car power. So if it's too fast, I can simply rotate this dial and change how much power is output to the wheels. Channel 7 is an override switch. So if I flick this, I can then use channel 8, which is the car lights, to turn either the car lights on or off. And if the override switch is off, that way the car has control of the lights. Same for the volume. If I switch the override on, I can then turn the volume right down if it's too loud for a public space or something like this. A pretty key member is channel 9, which is a 3-way position switch. And I want to have 3 different levels of control. So full RC mode is currently in position 0, steering only to the car, or steering and speed control to the car. So if at any point I don't like what my son is doing, I can flick this back to the first position and I own the car again, which I think is pretty cool. Channel 10 is open, but I'm thinking something to do with obstacle avoidance so that I can turn it on and off. This remote does also provide fail-safe values, but we will leave this for a future video. Let's switch over and now look at the receiver hardware. The most important point is that your receiver must be able to transmit iBUS data. And for the Flysky RC, please ensure that you buy the package with the FS-iA6B receiver. Otherwise, it's not going to work. It's a 5-volt receiver, and during testing, I regularly had a brownout with the ESP32, which is where the power supply drops below the minimum level for the chip to operate, and so it just resets. So I'm now powering the receiver independently with this cheap 3-amp buck converter, which is obviously set to 5 volts. We have a common ground connection, so I've got the ground from the power supply and the ground from the receiver, both going to the ground of the ESP32. For the power, we're taking the 5-volt directly from the buck converter to the receiver itself. And for the ESP32, I'm using a logic level shifter or converter, which takes the 5-volt iBUS signal and drops it down to 3.3 volts for our ESP32. Just a quick safety message for our hip pocket wallets or purses. Please do not feed 5 volts to any part of the ESP32, as it will most likely damage the chip and you will need to buy a new one. It only accepts 3.3 volts. Now back to your scheduled programming. For our UART communication, I've decided to use the serial 2 on the ESP32S3, which is pin 17, which is TX or transfer, and GPO 18, which is RX or receive. But the iBUS connection is only working one way, so we only need pin 18, which is connected via this grey lead under the dev board. For the Flysky receiver, we just use the top row. Going from right to left, we have signal, 5 volts, and ground. We've still got our button, but we won't be using it today. So finally, let's update our project code. We do need to add our RCLink library. So let's go down to libraries. Let's search for RCLink. And then we're going to add this to the project and hit add. So for now, we won't add Arduino JSON. What we will do, however, is to change some things, and we're going to put some build unflags. So standard equals GNU ++11 and minus standard equals GNU ++14. So what this will do is strip out any default compilers C++11 or 14. And then within our build flags, we add another one. And we will use C++17. And this will come in handy just a little bit later. So let's save that. So the first thing we will do is include the RCLink library. Under here, we'll add some snapshot bus scheduling parameters. So here we've got the spin limit, and this is just how many times it retries before letting something else run. And as you can see by this comment, this field is simply yielding only when not within an interrupt service routine, and this keeps things fair. So the reason we're doing this is if you go back to the main.cpp, we had this optional yield and task yield section under here, and I'd like to get rid of that. So we're just putting it within our app config. We're then going to add a time base, which is a single source of truth for the entire project. So this is the monotonic microsecond clock, which just is far more accurate for working within an RTOS environment than a standard timer. That's probably a little bit over the top in terms of commenting, but what this does is set our loop interval. And under here, we will now add a remote control section called RCLink. And this is namespace RC. And here we can define what our RC roles are and their name. So the first, I'm going to say it's steering. And this is channel 1, which is right horizontal. The next is direction. Lastly, we will say RC declare roles for the RC and RC roles. RC link enum builder. Now under library, we can create a new folder. We'll call this RC listener. And we will create 2 new files, rclistener.h and another new file, rclistener.cpp. So we need to create a constructor for this class. Oh, I forgot the colon. And when we initialize this task, if no variable is received, it automatically configures the period of the loop to loop milliseconds. We then have 2 other methods. We have a begin method, which configures our RC link. And then of course we have our standard task trampoline. Under our private variables, we of course have our main run loop. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. There's delay in ticks between the loop iterations. Then we have our rclistener.cpp. We have our generic constructor. Then we also need to configure our RC link. I would just do a quick copy paste. Then lastly, we can say RC link. This is how we build the RC link when we're not using JSON. We create a basic build configuration. We map the roles that we declared in our app config file. We then set our axes. So we can say that the steering axis has raw data points of 1000, 2000, and a middle point of 1500, has a deadband microsecond of 8, and its values go from -100 to 100. The switches are slightly different, but work in exactly the same way. It has raw levels and the values which the switches utilize. So in this case, 0 or 1, or in the three-way switch, the case of also 2. Lastly, we have our main run loop. Address of last, loop, ticks. And that's our pace loop. We should also update our other tasks. So state manager. So after bus, add our period microsecond. We also want to update this so it uses the abstract class instead of a concrete class. So we can just say iButton handler. It'll be the same. Input bus is the same. And then we can add a tick type loop ticks variable, which is initialized to 0. Now let's look at our state manager.cpp. Everything else is the same, except that we can get rid of this now and just say loop ticks. I think I forgot to do it in here. Okay, that's better. Let's do exactly the same thing with power drive handler. Because we've got input types, I also don't need these two libraries to be declared. I had to quickly fix this one. So we can go into power drive handler now. So that's all looking pretty good. Let's close all these. We'll now edit the main.cpp and clean it right up. So the first thing we can do is completely remove all these libraries. Because we've moved our universal button and ESP32 motor control into the individual libraries, we shouldn't need these either. And then we could include our RC listener. Now next we need to define our constants and type definitions for RC listener. There we go. Now we still have the starting of our serial monitor. We still have a shared input bus. We still have our button setup. We still have our motor setup. We still have our managers, but we need to include a third one, our RC listener. We could, if we wanted to, go down to tick and say that this is test short or test long, or even loop millisecond, but this is the default. We also need to say, let's set it to begin. And this configures the RC link. Let's then copy and paste this one. So we'll put all the listening tasks on core 0 and all the handling tasks on core 1 just for now. I think that's all we need to do. Let's save that and see if it compiles. Great, so that worked. So let's send it across to the ESP32 and see what it does. Here's our function printing every 250 milliseconds. I can adjust the steering. I can adjust the direction. Got the speed, indicators, got my volume, my power, got my override, my lights, my mode 0, 1, or 2, and my obstacle avoidance on or off. So it works really well. So there you go, a pretty simple solution for all your future RC projects. All the code can be found on the Little Man Builds GitHub page, link in the description, and if you've got any questions or queries, please feel free to drop a comment below. Of course, please consider subscribing and definitely smash that like button. See you in the next one.